N1 ddt of the magnetic flux through one turn. Right? That's E1. Now, if you consider the secondary coil, it has N2 turns. The EMF induced over there will be minus ddt of the magnetic flux through coil number 2. Right? So that's minus ddt. And what is the flux through coil number 2? That's the second one. It will be the flux through one turn, magnetic flux through one turn of that other one times N2 turns, because coil number 2 has N2 turns. Yes, the total magnetic flux through this coil over here will be the magnetic flux through one turn multiplied by the number of turns. So this E2 equals N2 with a minus sign here, ddt of the magnetic flux through one of those turns. So you have this for coil number 1, and you have this for coil number 2. Now, if so, a little aside over here, just a little aside. Chapter 31 is on a voltage source like this connected to a resistor, and then what's the current through that resistor. And then there's another section where you have a voltage source like this connected to a capacitor. Then what's going to be the charge in the capacitor. And then there's another section which has a voltage source like this connected to an inductor, which we're going to learn in chapter 30. And then you get the current in the inductor. And then there is a circuit where you have a resistor, a capacitor, and an inductor all connected in series to a voltage source like this. And then what's the current in the circuit? And so there's a lot of, this is the voltage source that you consider in chapter 31. Right? But we're going to skip that because we don't have time to cover all of that. But anyway, it's on AC circuits. Now, you'll see that the area of this coil over here, the area of each one of these turns or loops, this area is the same as this area. And if you manage to channel all of this magnetic field through coil number 1, if all of this magnetic field over here is channeled successfully through this coil over here, then same magnetic field, same area, then the magnetic flux through each turn is going to be the same. So if you take this equation, E2 equals minus N2 ddt of the magnetic flux through one turn, and you take the equation E1, the other equation, equals minus N1 ddt of the magnetic flux of just through one turn. If all of this magnetic field goes through there and this area is the same as that, then the magnetic flux for each loop, for each turn, are the same. And if you divide these two equations, then the minus signs are going to cancel, and then this term is going to cancel that, and you just get E2 over E1 equals N2 over N1. And that's the same as this equation. I mean, it's as simple as that. The easy result to remember is that with an AC voltage source, you can transform the voltage. You can step it up, you can step it down. Okay? In electrical power plants, they produce current, and in a circuit, right? By changing the magnetic flux through a coil, and the current is produced, or the voltage is produced, and before they send that voltage out to the cities, right, to be used in the buildings, houses like this, it turns out that less energy is lost in the transportation of that energy through, from the power plant to the cities if you use high voltages. And so, right next to the electrical power plant, there are these big transformers that step up the voltage to 100,000 volts, 150,000 volts. And then it gets sent to the cities. But then, when it arrives over here, you don't want 100,000 volts coming out of these wall outlets. So you'll see, like in the older cities like Costa Mesa, you might see this wooden posts on the sidewalk and a big heavy metal case at the top. That's a transformer to step down the voltage. And I wouldn't be surprised if the building itself, like maybe, as you go outside over here, so there's like a section over there, right there, like, as you go down, as you are gonna go down the stairs, there's like a area over there that you may wonder, what is that for? I wouldn't be surprised if they have transformers in there to then transform it back to 120 volts. Transform it down, step it down to 120 volts so that we can use our visible outlets. Okay, so I meant to bring something. I actually brought something the other day, and I meant to show you, but we finished class, we left, and then one of you said, "Oh, you didn't show that." And so let me go get it. I'll be right back. Hopefully I'll find it.